Welcome to our presentation on dimensional modeling. Today, we'll explore how to transform entity relationship diagrams into star schemas using a food delivery platform database. We'll delve into the intricacies of modeling data for entities like customers, restaurants, orders, deliveries, and payments. Let's get started on this insightful journey into data architecture. Welcome to our session on dimensional modeling. Today, we'll explore key concepts such as facts, dimensions, and grain. Let's dive into the vocabulary and techniques that form the foundation of dimensional modeling. In this section, we'll explore why businesses use two distinct models, the model and the dimensional model. The entity relationship model, or online transaction processing, is designed for running live applications. It's optimized for writing data quickly and safely, ensuring each order is saved correctly. This model is normalized, meaning there's minimal data duplication. On the other hand, the dimensional model, or online analytical processing, is tailored for powering dashboards and reports. It's optimized for reading and summarizing data across millions of orders, using a denormalized structure for fast and simple joins. This model helps answer questions like, what were our top 10 restaurants by revenue? Both models serve unique purposes, and a data warehouse benefits from having both to address different business questions effectively. In this section, we'll explore key concepts of entity relationship modeling vocabulary. First, an entity is represented as a rectangle in the diagram, such as customer, orders, or menu item. Attributes are fields within a table, like total price or veg n veg. Relationships are depicted as lines connecting two entities, for example, customer places an order. Cardinality describes the nature of these relationships, such as one-to-one, one-to-one, one-to-many, one-to-n, or many-to-many, m to n. The primary key is crucial as it uniquely identifies each row, like order_ID in the orders table. Lastly, the foreign key links to another table's primary key, such as orders.customer_ID. Understanding these elements is essential for effective data modeling. In this section, we explored the 18 tables across 4 business domains crucial for our data model. Starting with customer and address, we have tables like customer, user_address, gender, cart, and cart_items. Next, the restaurant and menu domain includes restaurant, restaurant_owner, restaurant_cuisine, cuisines, and menu_item. Moving to orders and payment, we cover orders, order_items, payments, refunds, and order_cancellation. Lastly, delivery and feedback involves delivery_partner, delivery_details, and reviews. Each table's primary key is highlighted in bold, ensuring unique identification, while foreign keys link to primary keys in other tables. Our goal is to transform these into a cohesive star schema, simplifying data analysis and reporting. This approach will enhance data accessibility and streamline business insights. In this section, we delve into the core components of dimensional modeling. At the heart of this model is the fact table, which records measurable business events. It serves as the central hub in a star schema, containing numeric measures and foreign keys linking to each dimension. Dimension tables provide the context for these facts, detailing the who, what, where, and when aspects, primarily using text for filtering and grouping. The grain is a crucial concept, defining what a single fact row represents in a concise statement. Measures within the fact table can be additive, like line amounts that sum across any dimension. Semi-additive, such as daily balances that sum across most dimensions but not time. Or non-additive, like delivery time minutes, which are averaged. Understanding these elements is essential for effective dimensional modeling. Let's delve deeper into dimensional vocabulary. First, we have the surrogate key, a system-generated key used as a primary key for dimensions, replacing the operational natural key. Next, the degenerate dimension is a value without its own attributes, stored directly in the fact table. When comparing star and snowflake schemas, the star schema involves a single join to flat dimensions, while the snowflake schema normalizes dimensions into subtables. A conformed dimension is built once and reused across multiple fact tables, ensuring consistent results. Lastly, the slowly changing dimension strategy manages attribute changes over time. Type 1 overwrites existing data, whereas Type 2 retains historical data. Understanding these concepts is crucial for effective dimensional modeling. In this section, we delve into the first two steps of the four-step design process for dimensional modeling. Step 1 focuses on the business process, specifically order fulfillment. Here, a customer places an order for food from a restaurant. This order is then prepared, paid for, and delivered, encapsulating the entire transaction lifecycle. Moving to step 2, we define the grain. This involves determining the level of detail for our data model. For our scenario, the grain is set at 1 row per menu item line within a customer order. This represents the most granular level available from the order_items data, ensuring detailed and precise data capture for analysis. Understanding these steps is crucial for building an effective dimensional model that accurately reflects business operations. In this step, we focus on the dimensions selected for our model. First, dimension date captures the order date from orders. Next, dimension customer includes customer details and gender. Dimension restaurant encompasses restaurant information, owner, and cuisines offered. Dimension menu item is straightforward, representing the menu item itself. Dimension delivery partner identifies the delivery partner involved in the transaction. Dimension address records the user's address details. Dimension payment method tracks the payment methods used. Lastly, dimension order status provides insights into the order status and any cancellations. These dimensions are crucial for creating a comprehensive and insightful data model, allowing us to analyze various aspects of the order fulfillment process effectively. In this section, we focus on the measures we capture in our dimensional model. Starting with the order line, we track quantity, unit price, and line amount. These metrics are crucial for understanding sales performance. Next, we have charges, which include tax amount, discount amount, delivery fee, and net amount. These help in analyzing the financial aspects of transactions. Post-order measures capture refund amounts, providing insights into customer satisfaction and return rates. Timing measures, such as preparation and delivery time in minutes, are essential for evaluating operational efficiency. It's important to note our modeling decision. We exclude cart and cart_items as they are pre-transactional and mutable. Instead, they could be used to create a separate cart abandonment fact table in the future. This approach ensures our model remains focused on actual business events. In this section, we focus on assembling the star schema, a crucial component in dimensional modeling. The star schema is designed to optimize query performance and simplify data navigation. At its core, it consists of a central fact table surrounded by dimension tables. The fact table captures quantitative data such as sales figures or transaction amounts, while dimension tables provide context like time, location, or customer details. This structure allows for efficient data retrieval and analysis, supporting complex queries and reporting needs. By organizing data into a star schema, we enhance the scalability and flexibility of our data warehouse, making it easier to adapt to evolving business requirements. Understanding the star schema is essential for data engineers and architects aiming to build robust analytical systems. Let's delve into the fact_order_line table, a crucial component of our dimensional model. The grain here is defined as one row per menu item ordered within a single order. Each row is uniquely identified by a system-generated surrogate primary key, the order_line_key. This table includes 8 foreign keys, each linking to a different dimension table, such as date_key and order_status_key. For traceability, degenerate dimensions like order_id and order_item_id are included without needing separate tables. Additive measures such as quantity, unit price, and line amount are safe to sum, providing insights into total sales. Currency amounts like tax, discount, delivery_fee, net, and refund are also additive. However, prep_time_minutes and delivery_time_minutes are non-additive and are more meaningful when averaged. This structure ensures comprehensive analysis of order details, supporting robust, data-driven decisions. In this section, we explore the transformation from operational tables to a data warehouse structure. The source. Online transaction processing tables include order_items, orders, payments, delivery_details, and refunds, which are consolidated into the fact_order_line table. The orders.order_date is mapped to the dim_date table. Customer and gender data are organized into the dim_customer table. Restaurant-related information, including restaurant, restaurant_owner, and restaurant_cuisine, is structured into the dim_restaurant table. Menu items are captured in the dim_menu_item table, while delivery partners are categorized under dim_delivery_partner. User addresses are stored in the dim_address table, and payment methods are detailed in the dim_payment_method table. Lastly, orders and order cancellations are tracked in the dim_order_status table. Note that carts, cart_items, and reviews are excluded as they represent different business processes. Today, we'll explore two approaches to answer the question, what was our total revenue by cuisine by month last year? First, consider the entity relationship model approach, which involves over 6 joins. This method requires navigating through tables like orders, order_items, menu_item, restaurant, restaurant_cuisine, and cuisines, along with customer and date filters. Each query execution repeats this complex path. In contrast, the star schema simplifies this process. Here, you only need one hop per dimension. The structured query language query demonstrates this efficiency. It joins fact_order_line with dim_restaurant and dim_date, grouping by cuisine and month to calculate revenue. This streamlined approach not only reduces complexity, but also enhances performance, making it ideal for quick insights. Understanding these differences is crucial for optimizing data retrieval in dimensional modeling. Let's dive into some practical exercises to solidify our understanding of dimensional modeling. First, identify a many-to-many relationship in your source-entity relationship diagram. Determine which bridge table resolves it and how you would represent it dimensionally. Next, consider the reviews data, which was excluded from fact_order_line. Design a new fact_review table specifying its grain, dimension foreign keys, and measures. Now, think about unit_price. Is it additive, semi-additive, or non-additive? What implications arise if you sum it across all order lines for a restaurant? Additionally, consider delivery_partner.ratings. Should it be a dimension attribute or a fact measure? Present arguments for both options. Lastly, if a customer changes their delivery city, should dim_customer employ slowly changing dimension type 1 or type 2? Discuss the trade-offs involved in this decision. These exercises will enhance your ability to apply dimensional modeling concepts effectively. If you want to get real-time experience, work on real capstone projects. There are 3 capstone projects which you can solve. The link is given into description. We've covered the essentials of transforming entity relationship diagrams into star schemas, focusing on defining the grain, identifying dimensions, and establishing facts. Remember, starting with the grain sets the foundation for your model, ensuring clarity and precision. Dimensions provide context, while facts deliver the quantitative data needed for analysis.